Section P.6 is titled Rational Expressions. The word rational comes from the root word ratio, and ratio means fraction. So we're looking at things in fractional form in this section. In particular, a rational expression is a quotient, right, a fraction, of two polynomials. Its domain is the set of all x values that work in the expression. And what we mean by work is that they don't make the denominator equal to 0. So if we're looking at problem number 1 and it's asking us to find the domain, it's equivalently asking us to find all locations where the denominator would not be 0, and then say it, and to say it in that way. But in reality, what we're looking for then truly is where does the denominator actually equal 0. So if you take your denominator, you can set it to be not equal to 0. You could set it to be equal to 0. That would be fine too, and then change adjust your language in a minute. And we're going to solve this. So we're going to add our 5 to both sides and find out very quickly that the only problem spot for this function is when x is equal to 5, right? So when I write down what is my domain, what I actually write down is one of a couple things. So one way you can write it is that you can write out words. X is all real numbers. Where x does not equal 0. 5. That's one way you can write the answer. Okay, that's a verbal description, and it's perfectly reasonable. There's another type of description called set builder notation. So set builder notation does a curly brace, and we say my answers are all the x. That's what this notation is actually saying. I do either a bar, or your book actually uses colons, I think. It doesn't matter, they're just interchangeable notations. That colon or that bar is read as the phrase such that. Okay, so this is the x value such that, and we say x, make sure I keep with the notation your book has, does not equal 5. Okay, so it's all the x values that are not equal to 5 is that notation. There's one other notation that's called interval notation. I'm not going to go into it at length right now, but if you've seen it before, you'll know what I'm doing when I do it, and you're welcome to use it. Interval notation starts with saying that it's from negative infinity to negative 5, union from negative 5 to infinity. What this actually tells you is that I have all values starting from negative infinity all the way until I get to negative 5. I use a parenthesis to say I can't equal negative 5. Union means that I also have in my answer set what follows. I do another parenthesis because I still can't equal negative 5, and I can continue on to infinity. So it doesn't matter to me what notation you use. Whatever feels the most comfortable, maybe whatever you've used most recently, you can use. Number 2 feels a little bit funny because the description that I said to start with when I said these were rational expressions said that they were a quotient. And you do not see a fraction in this particular expression, right? There is an inherent fraction there because you can always write something over 1. So this is a rational function. It's just not a very exciting one. And particularly, you might recognize what this actually is an equation for. Does anybody know? If you were to graph this, what it would look like. Yeah, Tiffany's drawing it. It's just a line, right? This is not an exciting function at all. It's just a line. But sort of in the effort of making it not exciting, it makes it really easy to work with. Because what it means is that I don't have a denominator to worry about equaling 0, right? Or you can say I've got a denominator, it's 1, but 1 is never equal to 0. So what happens on this one is that just x is all real numbers. You get everything. You get all of them. In interval notation, you would do something like negative infinity to infinity, if you're familiar with that. I'm not going to keep using interval notation simply because the book's not talking about it significantly here, but if you know it, you're welcome to use it. Okay, so number 3 definitely looks like a fraction from the get-go, right? And there's quite a lot going on in the denominator of that fraction, at least as it compares to the first 2 examples, The first example was just very simple. I could set it not equal to 0 or equal to 0, solve it very straightforward. This one right here, not so much. Okay, it's messier. And in particular, we're going to do the same thing. It's just that it's harder to work with. So we're going to take the denominator and set it to be not equal to 0. And because it's quadratic, this means that we're going to have to factor it. We talked about factoring last time. So as we set these pieces equal, this one works very nicely to just use trial and error. And again, the reason I can say that and believe that to be true is because there's a coefficient at the very beginning of the x squared that's a 1. That's why it's nice to use trial and error. Because I can immediately just put x and x here. We notice at the end the sign's positive, so it means my signs match. And because of the x or the positive in the middle, both signs will be positive. So I have positive and I have positive. 2 only can come about by multiplying 2 and 1 together. So again, I don't really have any choices on this one. The factoring is very straightforward. Nothing else to try. There's really no trial and error here. There's just the only option that presents itself is this one. It's either going to work or not. And it does work. And then the reason I can tell you, or the reason I'm saying it does work, is because if you multiply the inner, you get 2x. And if you multiply the outer, you get 1x. And when you add them together, you get 3x, which is what's in the middle, right? So this works. So what am I going to do next? Well, I'm going to do the same thing I did on the last one. I just didn't have to do it for 2 pieces. I'm going to set each part to be not equal to 0. I'll subtract my 2. So this finds that x cannot equal negative 2. I can subtract my 1. I'll find that x cannot equal to negative 1. If you wanted to really confirm that those do, in fact, solve this equation, you could take negative 2 and plug it in here, and you'll see that it's 0. You do the same thing with negative 1. So as I'm looking at how I could write my notations, I've got a couple of options. Again, I'm going to ignore the interval notation from here on out, but I can say all x, where x does not equal negative 1 and negative 2. It's one option. If I want to use set builder notation, I would do x such that, and do the same thing, x does not equal negative 1 or negative 2. Works very nicely. All right, so that's going to sort of end our discussion of domain. Any questions about domain before I shift to topics?
Can I ask you in a second how to do integral notation on number 3?
Yeah, we can do that. So let's take a look then at what happens when we look at the next set of directions. This talks about simplifying. So in a very real way, we're going to be doing kind of like what we did here on number 3, where there's factoring going on when I'm doing simplification. If there's factoring in the numerator, I can do that. If there's factoring in the denominator, I can do that. If it's just one or the other, I can just do the piece that I need. So we're going to take a look at what we have, and I'm going to start with factoring the denominator. Again, this particular denominator factors very nicely with trial and error because I've got that coefficient of 1 before the x squared. So I'm going to use trial and error and do x and x. What are my signs? What? Right, they have to be different, otherwise it will not get a negative 10 at the end. So I need 2 numbers that multiply to give me 10, but their difference, or their subtract, to give me 3. Okay, so you want negative 5 and positive 2, and we will double check to make sure. Does that in fact give me a negative 3 in the middle? Yes, it does. So that is the correct factoring. Now, if one of these factors actually matched what was in the numerator already, we wouldn't need to do anything with the numerator, but it doesn't quite match, which means I need to consider whether there's any factoring in the numerator to be done, and there is something. What can I do in the numerator as far as factoring is concerned? Right, I can take out a negative 2. And if I take out a negative 2, what will I be left with? Close, x plus 2. Yeah, x plus 2. And in fact, at this point now, these reduce, right? Now, if the question had been on here to find the domain, I would still not be able to have the x plus 2 equal to 0, even though there's canceling going on. I still couldn't have x plus 2 equal to 0. In other words, x could not equal negative 2. Because it still gives me the 0 on the denominator even before it reduces. I happen to also get a 0 in the numerator, but it doesn't just disappear. What you might remember if you've seen something like this before is it creates a hole in the graph. But this question is just asking me to simplify, which means I can reduce them out. And I can write my final expression as -2 on top and x minus 5 on bottom. Any questions on that one? What type of factoring, we'll just start with the denominator, do you notice on number 5? It is a difference of squares. Excellent. So let's do the denominator first. Not because we have to, but because I just mentioned that one first. So it's a difference of squares. How will the difference of squares a squared minus b squared factor? A plus b and a minus b. Fabulous. What about that numerator? Yeah, it's a difference of cubes on that one, right? So you have a formula for that. In fact, it's even in terms of a and b. It has a binomial term and it has a trinomial term. Remember, the binomial term matches what's already there. We just remove the cubes. So the binomial has an a minus b. The trinomial has an a squared and a b squared. They're both positive. In the middle is the opposite sign, so it's also going to be a positive. That is, it's the opposite of the binomial term. And then it's the a and the b multiplied, so I have ab. So I do have the a minus b's canceling out. And I mentioned this last time, but let me mention it again. It's tempting to say, well, maybe this will factor. It won't, all right? When you're working with a sum of or difference of cubes, the other piece, the trinomial piece, will never factor. So I don't have to try. That's good news. It means the problem's over. So my problem is actually giving me the simplified expression a squared plus ab plus b squared over a plus b. That's this as simplified as I can get. Okay, very much related to simplifying is our next step in the sense that I still need to utilize a lot of the same properties and pieces. We're going to do multiplication and division. So one of the things you'll remember about fraction multiplication, of course, is that you can just multiply across the top and multiply across the bottom, and that's true. You don't need common denominators or anything, in other words. But it's often easier to reduce as you go instead of to simply multiply across the top, multiply across the bottom, and then reduce at the end. It keeps things smaller. So I can look within a fraction, right, the 14w over the 51y. I might have the ability to reduce something here. Or, and the same thing with the 3w and the 7y. Or I can look across the diagonals, and it doesn't matter in which order I look at any of those things. So if you notice one right away, like the 14 and the 7, you might notice those right away as being reducible. You can just start there. So in other words, 14 and 7 both reduce or divide by 7. So we can reduce those right at the very beginning because it's very clear to us that we see that one. Right? It's a 2 and a 1. 3 and 51 actually reduce as well. Now 51 may not be one of those ones that you immediately recognize as being divisible by 3, but there's a very cool property of numbers that are divisible by 3. Has anybody heard how you can decide if a number is divisible by 3 easily? Say that louder for me. You're right. And not only does it work for 3s, it works for 9s. So 5 plus 1 is 6. Is 6 divisible by 3? Then 51 is as well. Now, that doesn't help you knowing maybe what it is. Your calculator can do that for you. That's fine, but it will work. And it works no matter how many digits your number has. So if you're dealing with a 4-digit number or something like that, you can do the same thing. And it does work for 9s. 5 plus 1 in this case is 6. 6 is not divisible by 9, so therefore 51 is not divisible by 9 either. But they are divisible by 3. What is 51 divided by 3? It's 17. Very good. And at this point, there's no simplification I can do with the variables, right? Across diagonals or within a single fraction. So now I will just multiply across the top. 2 times 1 is 2. And w times w is w squared. The denominator, I have 17 times 1, 17. And then y times y is y squared. Cool?
So, how would, like, in order to, like, show you, like, if this was all equal to 20 and, like, nothing simplified like that, would we just go?
You just would multiply star across, yeah, you would. Generally speaking, things simplify quite frequently. It's very uncommon to see something where nothing does simplify when you're being asked to multiply or divide. I would say probably, this is a made-up statistic. It's one of those things that people do, right? You know, I would say probably 95% of the time something's going to simplify as you're working with it, because somebody created the math book to do it that way, right? Yeah. The next one's really messy. Oh my goodness. It's also important that you notice that it's not multiplication, it's division. All right? So do you remember what happens when you divide fractions? How do you change that? Yeah, you multiply by the reciprocal, and it's always the reciprocal of the second fraction, okay? Sometimes I have students who just like to flip something else, okay? We always flip the second fraction. As I'm doing this, I'd actually like to factor as I go, because I don't really want to write this thing down 6 times. That's not in my best interest time-wise. The first one right here, if you need the AC method or you want to slide and divide, that's fine. I'm going to use trial and error most of the time because it's usually quicker. I can usually sort of reason through which one it might be, and I can eliminate some of the time involved. But if that doesn't help you thinking through it, please use another method. 3a squared would be 3a and a. I have the sign at the end is negative, which means I have one negative and one positive, and I don't know which one's which right now, so I'm just going to put them in there. I have the number 4 at the end, so one option is like 4 and 1, but that's never going to give me, I'm sorry, and that might give me the one in the middle, because 4 and 3, so if one of them's 4 and one of them's 3, they're one apart. So it does seem reasonable to try the numbers 4 and 1. So if we do 4 here and 1 here, then I get negative 4a and I get positive 3a, which is really close to what I wanted, right? I should write it so you can see it a little bit better. This is negative 4a and it's positive 3a. The problem is that it's the right number. It's got a 1, but it's negative. Yes, when I add them together. We talked last time about when that happens, what does it mean we need to do? And it just means that we need to change the signs. So this one needs to be positive, and this one needs to be negative. And then it will work out to being a positive a in the middle, because now my 4 is positive. You can do a couple of things in the denominator. If it bothers you that the a squared's not at the front, because it kind of bothers me if I'm being perfectly honest with you, you can simply rewrite it and pull the negative out as you go. So let me actually take just a step to do that, and I'll shift this over so we can kind of do it to the side for the second. If I did that and I pulled out a negative as I rewrote, this negative 2a at the beginning now is a positive 2a squared. In the middle, the negative a is now a positive a. And then the 15, which was positive when I pull out a negative, is now negative 15. So kind of a scratch work aside. It fits better within the construct of the way we normally see things, okay? If you're comfortable with dealing with it the other direction, it's okay. You can do that too. But this is a viable option. So it gives me a negative at the beginning, and then my 2 sets of parentheses. The 2a squared gives me a 2a and an a. And then the sign being negative at the end gives me a negative and a positive. And again, it's arbitrary. I'm going to stick them in there. I'll move them if I need to. What are some different things that I could multiply together to get 15? What are some options I have? 1 and 15. What else? 3 and 5. Whoops, I didn't mean to write 15. I meant to write 5. 3 and 5. 1 and 15 seem highly unlikely to be helpful because 15 is a very large number compared to the fact that I want a number 1 in the middle, right? So probably just by reasoning, it seems reasonable to try the 3 and the 5 instead. So I'll try 3, I'll try 5, and if I don't like the way they put in there when I put the 3 first, 5 second, I'll switch them and see if that helps. So let's check. This is negative 3a. On the outside, I have 10a. That did not work, right? I need the number 1a in the middle, or the expression 1a in the middle. So that arrangement was not a good choice. So I'll switch where I put my 5 and my 3 and see if that helps, because my numbers were so far off. In the middle now I have negative 5a. On the outside I have positive 6a. Yeah, that one worked, right? So we're good to go with that one. So now I've got the denominator of the first fraction simplified, or factored anyway. Okay, the next one, I'm actually going to start with this denominator because it's going to be moving into the numerator, right? I'm flipping this to be multiplication. So I'm looking at this expression right here as I'm factoring. You might recognize this as a special factoring form. It's not one that I usually talk a whole lot about because it's not necessary to identify it. But you might have seen it before. It's actually called a perfect square. Not difference of square, but a perfect square trinomial. And the reason that it has that property is because what you'll notice is that in the middle here, this is a number squared, right? 4 is 2 squared. The 25 is 5 squared, okay? And then we have this 20 in the middle cropping up, which happens to be 2 times 5 and doubled. That's a property that works out when I have perfect squares. However, at the very least, because I noticed that there's a 4 squared, or a 4 at the beginning, and that's a number squared, and the 25 at the end, it's really nice to be able to try and see what happens when I split it up into its perfect square components, right? So 4a squared is 2a and 2a, and 25 is 5 and 5. And what can you tell me about my signs based on this particular problem? I'm sorry, say it a little bit louder. Okay, so there's a positive at the end, which tells me the signs have to be the same, right? They have to be the same. And the negative in the middle tells me that they have to be the same and negative. So my signs have to be negative. And then we need to check and see if we get 20. And if you'll take a look real quick, both of the inner and the outer terms are in fact negative 10. So I do get negative 20. So this is the factoring that I was looking for. So now we're going to do the same thing up here. 6a squared minus 7a minus 20. Okay, so at this point, that's not fun to do with trial and error. Agreed? But, can you remind me your name in red? Elizabeth. But Elizabeth kind of asked before, what if something doesn't factor out, right? And I said, it almost always does, right? Like that. We expect there to be something that factors out here. Like that's our anticipated result. So if we take a look at the kind of values that we already have showing up, we can give some pretty good educated guesses as to what might work out that will cancel. And we can probably do it also by recognizing that some of these things cancel already, right? So the 2a minus 5 and the 2a minus 5, one of those is going to cancel automatically, right? You see that across that diagonal. Nothing else at the moment. But it seems quite reasonable in this blank space down here that I'm going to end up with like a 2a minus 5, or maybe a 3a plus 4, or maybe an a minus 1. That's what I'm expecting to have happen, okay? Because it'll reduce. So let's take a look at what might happen. If, in fact, we do think, hey, I might have a 2a minus 5. Let's build around that and see if we can make something else correspond to that and work. So what do I mean? Well, this says 2a, and whatever goes in this spot where the a is has to multiply to give me 6a squared. So that would be a 3a. Right? I got to get 6a squared, so 3a times 2a is 6a squared. The signs have to be different because this is a negative at the end. So one of my signs is already negative. The other one is probably going to then be positive, and not probably, it will. It has to be. And now I need the number that multiplies by negative 5 to give me negative 20, and that looks like 4. Now, that's very friendly because I had a 3a plus 4 already, right? I do need to check to make sure the middle terms worked out and that I wasn't just sort of luckily guessing some pieces that don't end up actually working. So let's double check that that middle term actually gives me a negative 7a. So this piece right here, 4 times 2 is 8a. Well, that's this side because I'm running out of space. And then the 3a times negative 5 is negative 15a. Do I get negative 7? I do. It worked out. So again, it is reasonable to think that other pieces that I'm looking for in that denominator, even though it's a messier denominator to work with, are in fact going to cancel out. So there's that 3a plus 4. Here's that 2a minus 5. So what remains? Well, not a lot. That's actually the answer. Not a lot. Let's see. We have a minus 1 that remains right here. I need that to be a little bit darker. The a minus 1 remains right here. And the a plus 3 remains right here. There's one more thing that remains. Yeah, that negative that's the front of that denominator. So you can write that a couple of ways. I would probably just write the negative out in front, but you can put the negative in front of the top or in front of the bottom as well. So this is a minus 1 on top, a plus 3 on bottom. You don't have to have them parentheses. If you did, it would be fine. And this is my final expression. If you were looking in the back of the book, they might take that negative and like multiply it through the numerator and rewrite it as negative a plus 1, or multiply it through the denominator and rewrite the denominator as negative a minus 3. Not both, one or the other, but they might do that. Okay, that is definitely the most complicated one that we've seen. Any questions on that one? All right. Slightly different directions, leading us to something. Our directions here say they want us to take the expression x plus 2 over x minus 8. And they want us to convert it into an equivalent expression where my denominator is 16 minus 2x. So a couple things you might notice is that the denominator seems to be doubling something. I had an 8 in the original denominator, now I have a 16. I had an x and now I have a 2x. You might also notice that the direction changes, right? First the x was first and now the x is second. So a couple of things are going on. In particular, when we're working with this, what we're wanting to see is we're wanting to see that x minus 8 become the 16 minus 2x. And in order to do that, we're asking ourselves, what did I multiply by to make that happen? So what would I have to multiply by to make this happen? I'm going to use a dot, not a x. I didn't use that. What do you think? Negative 2 will do it. 2 doubles everything. And the negative changes everything positive to negative, everything negative to positive, or another way of thinking about it is it reverses the order of the subtraction. So I need to do the same thing on top to multiply by negative 2. So I now have negative 2x on top and negative 4. Most of the time we tell you at the end of a problem, make sure you reduce everything. That would not be helpful here because I actually changed something so that it was not in its reduced form because the directions said to change it into the form that I currently have. So I'm not wanting to reduce. This is in fact the solution that they're looking for. So why? Why would I want to do that? Well, the reason I would want to do that is because as we move into addition and subtraction, we do in fact now need our denominators to be the same in order to add or subtract fractions together. Okay? You don't need it for multiplication and division, but you do need it for addition and subtraction. So on the first one, you might notice that on number 9, that I don't even have a fraction on the first value. It's just negative 1. So the first thing I might think to do or want to do is to simply write it in fractional form. It's negative 1 over 1. And then I need to get a common denominator. Well, one of my denominators is 1. The other one is c. So if I multiply my denominator that's 1 by c, I will now have a common denominator. But as with anything for fractions, whatever I do to the denominator, I have to correspondingly do to the numerator. So what I now have is a negative c on top over c minus 3 over c. And once my denominators match, you didn't necessarily have to write the step that I just wrote down. But once my denominators match, I can combine the numerators into a single numerator, written as the subtraction, negative c minus 3. And my denominator, since they now match, is simply the denominator c. Now, it doesn't really combine much on this one, right? I mean, I just wrote it as a single fraction. I didn't actually have the ability to condense the pieces in the numerator. Sometimes you do and sometimes you don't. It just depends on the problem you're working with. And on this one, we didn't. So we stop right there. Next one's a lot more work. When I have quadratics in the denominator, just like when I had quadratics in the denominators for multiplying and dividing, it is not helpful to simply multiply the two denominators by one another. It isn't that it won't potentially work, but you've created a big giant mess if you do. And simplifying it is probably almost impossible at that point for you to do. So what we want to do when we're working with multiplication and division is factor denominators and numerators. We want to do the same thing to the denominators anyway when we're working with addition and subtraction. We want to factor them. So we're going to factor the denominators that we are given here. And I'm going to just factor them where they are. There's no reason to have to rewrite unless you just want to, which is fine. So in the first one, again, they have coefficients of 1, so trial and error is very nice. I have x and I have x. What can you tell me about the signs? What do they need to be? Different. So I need one negative, one positive in some order. I need two numbers that multiply to the 6 at the end and add a positive 1 in the middle. Yeah, so it's a -2 and a +3 to give me a +1 in the middle. And we'll stop right there on that one. We're going to remember to do the same thing on the second denominator. I have an x and I have an x. What are my signs on this one? Both positives. And I don't have a lot of choices. The number 3 is 3 and 1. And I don't even care where they go because it's both addition, right? And did you check the middle? Does it actually give you 4x? It does. Okay, so kind of going back to this question that Elizabeth, right, had earlier about what happens when things don't reduce. Your expectation at this point is that something from among these denominators is going to match. Does it? Yeah, it does. That's the expectation. If they don't, you've probably made an error. I mean, realistically speaking, there's probably something you've done wrong. One of them is going to match and the other one is not. In this case, they both have an x plus 3. So what I need to include is whatever they don't have. The first denominator does not have the x plus 1, so now it needs it. And it needs it both on top and on bottom. So I'm going to write it that way. The second denominator does not have the x minus 2, so it needs it both on top and on bottom. Okay, pretty good so far. Okay, the next news is maybe the best news you're going to hear all day. Are you ready? Are you ready? You guys aren't ready at all. I can tell. Don't care. You do not need to multiply the denominator out. Oh, come on. That's good news, right? You guys might have lynched me if I told you we're going to multiply the denominator out. Right? You said, no, thank you. We're going to leave it all in factored form. Now, we haven't multiplied the numerator, but we do not multiply out the denominator. And you can write the denominators, multiplications, in any order you'd like. Doesn't make any difference. But this is my new denominator for both fractions that I'm going to combine in a single fraction, okay? I need to multiply this x plus 1 times the x minus 1, though. I hope you recognize that that's a difference of squares. Okay? Now, if you don't recognize it, it's okay. It'll all come out in the wash. But I hope you're recognizing those things as you see them. We have to multiply first, outer, inner, last, and then reduce. So if you don't notice it, you'll end up having an x squared plus x minus x and minus 1. And of course, the plus x and the minus x cancel. If you happen to notice that it's a difference of squares, you can probably jump straight to the x squared minus 1, and that'd be great. This one's not a difference of squares. It's actually the same term twice, x minus 2 times x minus 2. There is a negative in the middle here, and I'd like to not deal with it at the same time because I think that I can get confused really easily if I try to. So I'm going to put the subtraction sign in a parenthesis, and then I'm just going to deal with the multiplication of the x minus 2 times x minus 2. Okay? So x minus 2 times x minus 2 gives me x squared minus a 2x minus another 2x and plus 4. So far, so good. All right, denominator stays the same. We don't need to make any changes to it. X plus 1, x minus 2, and x plus 3. I do need to combine the negative 2x's, and I also need to distribute this negative through. So I'm going to kind of just do some little bit of scratch work up here to try to clean the numerator up, because I don't really want to have to keep rewriting the denominator like 10 times. I just need to clean up the numerator. So I might go ahead and remember that this part at the beginning is x squared minus 1. And then this negative is going to distribute, so that's negative x squared. I have negative 2x and negative 2x, which is negative 4x. But then I have the negative in front, making it now a positive 4x. And then I have a negative times the 4, so negative 4. Those are the pieces of my numerator that have been distributed through at this point. And I can combine some things. Did I miss one? Yes, perfect. So the x squared and the negative x squared are going to add to 0. They're going to cancel out with one another. You bet. And there's another piece that's going to combine, though not cancel. Yeah, the negative 1 and the negative 4. And you don't have to write them at the end, but we tend to do so. Put that one second with the 4x at the beginning. Now, it is possible, though it doesn't happen frequently, it is possible that what I end up with right here, the 4x minus 5, will actually cancel with something that's in my denominator. So I do need to look and make sure. This one doesn't. But I need to double check. Okay? So 4x minus 5 doesn't have anything that factors out, doesn't match with anything perfectly in the denominator. So I'm done. All right, I want to present one more thing that shows up here. So this was a subtraction one. We could have done an addition one just the same way. Addition was even easier because I don't have to worry about distributing that negative through. So adding and subtracting are very similar operations here. The last thing I'd like for us to take a look at in this section are what are called complex fractions. Complex fractions are simply fractions inside of a fraction. Okay? Now, the reality is that they're really not any different than number 7. I promise I'll pull it back.
No, you're good.
They're not any different than number 7. They're just written differently at the get-go. Okay? Number 7 was a division problem. I just had the two fractions next to each other with the division sign in between. This problem is a division problem with two fractions, one on top of each other, with a division bar as a fraction bar in between. So if I recognize what's really going on here, this is really 9a over 35 divided by 6 over 25a. That's it. It's not any harder than that. There's just this recognition factor at the beginning. And what do we do when we divide fractions? We multiply by reciprocals. So the 9a over 35 stays the same. And the reciprocal of 6 over 25a would be 25a over 6. I've changed to multiplication. And now I look both within fractions and across diagonals. Somebody tell me something you see that reduces. Okay, 9 and 6. What can I divide both of them by? 3. So I have 3 and 2. What else? You bet. 25 and 35 both divide by 5, giving me 7 and 5. And I think that's it. So once you get to the point where you've reduced all that can be reduced, we multiply across the top, which gives me 15. I have two a's, so that's a squared over 14. And I'm done. Okay. Now, while it is true that I could also do the same sort of thing here with writing the division, this one poses something that's a little bit different than the last problem. In particular, each individual numerator and denominator of the large fractions themselves have one piece that's a fraction and they have one piece that's not. Correct? So there's actually a really nice simplification process we can use when that happens. Notice that the little denominators are both y plus 2. Does everybody see that? Yeah. So what I'm actually going to do is I'm going to multiply by y plus 2 on the top and on the bottom. I'm allowed to do that because I did it to the top and the bottom. The thing that you have to be very careful to recognize is that it has to apply to everything on the top and everything on the bottom. So in a very real sense, the y plus 2 multiplies by y, by this fraction, by this y, and by this fraction. The whole fraction, like this whole thing and this whole thing. Okay? So if I multiply the first one, the y times the y plus 2, I have y squared plus 2y. So here's where something cool happens. What happens when I multiply y plus 6 over y plus 2 by y plus 2? The y plus 2's cancel out, which is the whole point and why I want to do that. I am left with the single y, is there a subtraction sign? Subtraction sign, and then y plus 6 in that numerator. That's what I'm left with. Now, let me show you one other thing you could write, because I don't really like the way I've got all my arrows and everything drawn here. I think it's helpful to see that that's what I'm doing. But I think it's actually more helpful for me to write it like this. I'm really multiplying the y plus 2's like this. So when I get over here, these cancel and these are going to cancel. So each piece individually gets multiplied by y plus 2 in a distribution process. But this, I think, allows me to do my cancellation in a way that's a little more clear. So on the bottom, I still have y squared plus 2y. I have subtraction. My denominator, y plus 2 is canceled, leaving me with 4y plus 15. It's still not done, but it looks better than it did before because I don't have fractions inside of fractions. Okay? I do still need to distribute those negatives, combine like terms, and I still have to check and see if there's any factoring and reducing that can be done at that point afterwards too. So I'm not done by any stretch of the imagination, but I've made some headway. So I have y squared plus 2y minus y and minus 6. And then y squared plus 2y minus 4y and minus 15. So that's the distribution. So on the top there's y squared. 2y and negative y gives me positive 1y. And then my negative 6. The denominator is y squared. 2y and negative 4y gives me negative 2y. Good job. And I have minus 15. Neither one of these are terribly difficult to factor, though. So that's kind of nice. We came to a point where the factoring is going to be pretty simple. And we're looking to see if anything reduces when I factor. So I have y and I have y. What are my signs? Opposites. So a negative and a positive. Two numbers that multiply to 6 and add to 1. Yeah, negative 2, positive 3. Denominator, y and y. What are my signs? Yep, same as before. Well, they're opposite signs, but they're the same as the numerator. I have one negative, because it's a negative 15, and one positive. So the negative 15 at the end tells me my signs have to be different from one another. And then I need 15. Two numbers that multiply to 15 add to negative 2. Negative 5 and positive 3. Does anything reduce? Yeah, so this is one of those cases where it might not reduce, to be honest, at this point. We did a lot of work to get to this point. This one happens to reduce. So my final answer is actually y minus 2 over y minus 5. Yes?
I don't know if this is wrong. Does it normally work out, though, like, so the negative 6 and the negative 15, before we factored, were already reducible by 3? So, I mean, not that you would reduce beforehand, but is it plausible to guess that they will reduce after you factor?
It depends on what the other pieces of information are. It doesn't always work that way. That's a good guess. I don't want you to try and sort of think through things piecewise, though, because factoring takes it out of the entire expression, not just one piece of it, a single term. And so you can get led astray very quickly if you look at pieces too closely like that. Yeah. All right.